And what I've got here, this is from the IAEA. Oh, by the way, all these slides are official slides. Not me. No, 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 no. I'm not making this up. This is their evidence, okay? I have to look at it a bit differently than they do. But, not to worry, it's their work. This is the Danube River, the blue Danube. And this is a nuclear power station in Romania called Chernobyl. It doesn't really matter. But this is a study that they did. This is a can-do reactor.
The Canadian.
That's right. In our friendly Democratic Republic of Romania, not. Anyway, what happens here is that they've modeled the discharge of 10 terabecquerels of tritium over a period of 24 hours. This is what the model does, right? And these, and so you can tell that the wind comes from the southeast and blows to the northwest. Yeah? See that? And these are tritium doses from ingestion, from eating contaminated food, tritium-contaminated food. And you can see that where it's red, you get fairly high doses, up here, lower doses. But this gives you an idea of the plume that happens when you open up the reactor for taking the old fuel out, putting the new fuel in, like that. Next slide. This is the same sort of thing, but the wind is different. Here, it's changeable. First of all, the wind is like this condition, then it's like this, and then it's like this. And not only that, it's a very low wind speed. And look what happens. The doses get much bigger. This is organically bound tritium in cow's milk. Big doses because of the weather patterns different. Gives you an idea of what happens. Now, as a result of that, we've campaigned, in Britain, we've campaigned for the nuclear operators to tell people when they're going to open their reactors to refuse. We said, well, look at this pregnant woman living nearby. Tell them that they should maybe go away for a few days. No, they won't do it. Well, will you do it when the wind's streaming out to sea, please? They won't verify that. Will you do it at night time when people are in bed? No, they won't verify that. Bastards. That's the only word you can use. I don't like swearing, but it makes me angry that they don't do that. Because they're not honest. They know all this is happening, but they won't play straight with us about it. Go on, next slide. Again, this is an official CNSC. You might say, well, yeah, this is all very theoretical, and you haven't got any direct evidence of tritium and air concentration in nuclear power stations, do you? You're just making it up, aren't you? This is their data. This is distance from the reactor, again on the x-axis, and these are air concentrations of tritium. And you can see, the closer you get, the higher the concentrations. And these are all Canadian reactors. You can see Bruce, Pickering, Gentil, Littoral, and Darlington. Canadian reactors. So if you're living near a very near a reactor, these are the air concentrations. And anything above this is worrisome. Now, it so happens that Pickering is about 15 kilometers from downtown Toronto. Honestly, I think it's terrible. I really do. I don't know what to say to people who live in Toronto. I really don't. Go on, next slide. Just about. And then you might say, well, hang on, Ian. Okay, there's tritium in the air concentration. That doesn't mean there's any tritium in food. Here we go, tritium in food. And their results. I've finished these graphs. Anyone can do the same. Again, you can see x-axis distance from the reactor, this time logarithmic. Again, and y-axis, again, logarithmic. And you can see the closer you get, the higher the concentrations. For those people who are mathematically inclined, this is about 20 kilometers here, click. And you can see it's a straight line. Slope of about 2. Which, in a log-log table like this, a log-log chart like this, tells you that, that the closer you get, there's a doubling of basically inverse square law. And that's what this actually shows you. It's very similar to the increased risks that I showed you earlier on. There was food concentrations and risks match each other the closer you get to the reactor. Very good evidence of that. Go on the slide. So people are going to say, well, what's tritium? Well, we don't have a lot of time for that. Just very quickly. It's the radioactive isotope of hydrogen. You all know the hydrogen, we don't. It's the lightest known element. One proton, and got one electron going around it. If you put a neutron in, that becomes deuterium. If you put in 2 neutrons, it becomes tritium-3. It's mainly in the form of tritiated water. In other words, you know how hydrogen, water is H2O, 2 hydrogens, and one of them is radioactive. So what happens at Pickering and Darlington and other Canadian reactors is that humongous amounts of tritiated water are shoved out in the atmosphere. Huge amounts. Hundreds of terabecquerels. Terabecquerel is a trillion. Hundreds of trillions of becquerels. The becquerels of disintegration per second. This is radioactive water. Well, we are water. We're 60% of water. And this radioactive water gets everywhere in the environment. Anywhere that is, any biota at all, plants, animals, whatever, us, gets tritiated to certain levels. In other words, we become radioactive. This has got the property here of getting into human beings, and we metabolize it, and it gets bound inside us as organically bound tritium, and giving us even bigger doses. Nasty stuff. That's what happens when you play around with stuff that we need. I often don't really worry too much about inert gases like xenon and krypton and argon, because we breathe it in and you get a little dose, not very much, and breathe it back out again. We don't use argon or krypton. It's slightly soluble in fats, but not very much. But water, bingo, yeah, we take it in heavily. Similarly with carbon dioxide and the radioactive carbon-14. Of course we don't notice it at all. Next slide. The thing about tritium is it's got a lot of unusual properties. Oh, God, it's just amazing the more you study it. Extreme ability as water, and exchangeability. It sticks inside us. Very short range, damage depends where it is. Many nuclear scientists describe tritium as weak, but it's actually more dangerous and strong radionuclides. So the result is that tritium models officially actually significantly underestimate the dangers of tritium. It's got the lowest dose coefficient of any radionuclide, when in fact actually it should be amongst the highest. Let me give you a little example of tritium. I worked with tritium when I was in Imperial, London. And we were using a tracer, tritium as a tracer, not very high quantities, a few kilobits, and putting it into a stream, not very much, a while, and then we were going to take it downstream and measure how long it took to get, a kilometre. We could have used a dye, but these guys were, radioactive nuts. They wanted to use tritium. So what they did was that they were larking about. It was April the 1st, I remember, April Fool's Day. And they said, and one guy said, I'm going to measure the tritium levels upstream. And everybody thought it was a funny joke until he found levels upstream. I kid you not. We couldn't believe it. Well, found downstream all right, but upstream. And I'm going to explain to you what it is. I hope you can come along with me in this. You have to go back to basic physics. All atoms are promiscuous and swap with other atoms. So if you've got an H2O molecule here and an H2O molecule here, and there's a hydrogen here and I'll say one hydrogen and one here, those two hydrogens swap. It's called molecular exchange. And the rate at which they swap is like it takes 10 to the minus 16 seconds for that swap to occur. So that means, the reason why it works with hydrogen is because it's the smallest known atom. All atoms do it, but at a much, much slower and less prevalent rate. With hydrogen, it's all the time, everywhere. So if you've got a bunch of water molecules, zoom all the way downstream, it goes jiggity, 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 like that, really fast. Within a couple of seconds, boom, it's gone. And that was what happened, it was going upstream. So the end result is that when tritium gets out of the environment, it goes absolutely everywhere.